what we are doing. It's a pleasure to have Shailesh. She's going to talk about probably approximately correct mathematical tasks. Go ahead, Shailesh.
Uh, Thanks for the kind introduction, Artan. And let me also begin by thanking the organizers for putting together such an interesting set of seminars. It's a really nice opportunity to learn what great things people are doing at BIMSA, and very motivating to try and contribute. So I'm going to talk about something called probably approximately correct mathematical physics. And of course, it's never a good sign when the title has two weasel words followed by a bold claim, right? So a better way of defining this would be to say machine learning mathematical physics. Um, but then no one would come. Okay, so let me tell you about my work. My work, and I'm just putting this right at the beginning, which is to get it out of the way as soon as possible. I work on applying neural networks to mathematical physics. Okay? And typically, or like the things that I'm thinking about most are about how to predict the topology or the geometry of maybe a Calabi-Yau manifold, which is very interesting for us in string theory, by quote unquote looking at it. And I'm going to explain what that means. Okay? And the second is actually finding quantum integrable systems by directly solving the Yang-Baxter equation, which I will show you in a moment. Okay. Okay, so like I said, I'm not really going to talk about the technical details of what I did. It's just like a couple of slides of illustration that look, this thing actually works. What I'll talk about are really the ideas that underlie such computations. And this is basically the question of what is the utility of computations that are probably approximately correct. So by probably, one means that we use statistical correlations to make predictions about some variables. Okay. And also, ideally, you don't want an oracle who will just tell you the answer, shut up and go away. You would need some estimate of how right or wrong you probably are in your prediction, right? Uh, Approximately, of course, because as I will show you, it obtains approximations to a ground truth. And ideally, these approximations can be systematically improved. Hopefully, once you have kind of gone through this whole process, what will happen is that it will help you generate an actual conjecture, which you can then try and prove or disprove. Okay? That would be like the holy grail, as it were. Okay, and correct? Well, yes, it should actually give you the right answers more often than not. Okay, so essentially, so the overall purpose of the talk is to address two questions, which is one, why is machine learning potentially useful if you're a practicing mathematical physicist, and why neural networks are in particular very useful. And what I'll show you in a moment, it's not super appreciated in general, but these are slightly distinct questions. And the question of machine learning and the question of neural networks are kind of entwined in each other in a way that it makes it a bit difficult to tease apart, but I'm going to try and do that. Okay. So why neural networks? So there's this thing called the universal approximation theorem. Sorry, these figures got messed up, but basically, I'm going to try and motivate for you the statement that given a function, a neural network can be brought arbitrarily close to that function. Okay, that's what I'm going to show you. So let's yeah. So let's start with the toy neuron. I mean, the picture that all of us have in our mind when we think of a neuron is that it receives an input, and after the input crosses a certain threshold, it fires, right? So basically, just the step function. And then, of course, the tunable parameters of this neuron are just very simple. It's just basically the location where it should fire, the threshold value, and the magnitude of the fire. It's fine. I mean, these are the only two pre-parameters in this game. Okay. So now, if you take the difference between two neurons, you get a pulse. And then, of course, we are done, because given any function, we can always approximate it by a series of bins. And for every such bin, I take that pulse and I put it together. And by the way, this is not a constructive proof. So if you actually train a neural network, this is not what it will learn. But at least at the level of plausibility, it's fine. Okay. So basically, this is the statement that if you have a neural network, you can kind of tune the parameters to approximate any function that you want.
Nice.
Well, yes, there are some admissibility constraints, but it also depends on the activation function and so on. So, yeah. Okay. Yeah. So, and the basic magic of neural networks is that the neural network adjusts its own parameters to fit the desired function. And that's what I'm going to show you. Great. So, like, here's a nice analogy to think about this whole problem. So, imagine that you're moving in function space. On the y-axis, you have some measure of how far away you are from the function you'd like to be. Okay, and x-axis, you have the neural network parameters by dialing which you're moving in function space. Okay, so and this is usually a positive definite quantity. Well, always, and then you move in function space and you kind of go down, and ultimately at some point you actually hit the point, the function that you're actually trying to learn, and then that thing is 0 over here. Okay. So this is of course very powerful when you don't know good ansatz for the function. So typically, many times in physics, we are trying to scan across function space, maybe to solve, say, a differential equation, or to solve maybe a problem in conformal field theory by using crossing symmetry, imposing certain constraints. But then you need to know, or you need to have some way of knowing what is a good basis to expand your function, or what is a good ansatz to take. So, for example, if you want to solve, say, the Coulomb problem in quantum mechanics, and you choose an ansatz of plane waves, it's going to be very difficult, although it is a complete set. Okay, so often the difficulty in arriving at solutions is simply that you don't know how to expand the function. How do you represent the function? And the claim is that because neural networks can approximate any function, you basically take whatever you want to approximate and model it by neural network. Is that fine? Okay. So here's one application. So to quantum integrability, and of course for this I'm going to kind of cheat shamelessly and say that anything that you don't understand here, please ask Bart over there, because this is kind of almost exactly what he talked about. So essentially, imagine that you have a quantum system. So and it has an infinite number of charges. So it's a very, very constrained system. And what we would like to do is to try and determine such systems. But one of the things that kind of just like we have to accept at the moment is that there is some function called the R matrix, which is a set of 16 functions in a particular case. So of course, I've written it as a 4x4 matrix, but nothing stops me from writing this as a 4-component tensor where each tensor takes 2 values. So I'm going to just write it like this. And this function actually obeys a certain set of cubic equations. So there are 64 of them because you have, I think, 6 free indices over here. They take 2 values each. So you have 64 cubic polynomial, so 64 cubic functional equations for 16 variables. So it's a highly over-constrained system. Okay, and the claim is that if you want, one of the great difficulties is that given such a set of equations, how do you solve them? And this is not the only equation to be solved. Great. So of course, then if you want to do this using neural networks, then an obvious thing to do is that you take each of those R matrix functions, all of these, the 16 neural net and 16 functions, you take 16 neural networks, and then you say that, look, the Yang-Baxter equations are really constraints on the R matrix functions. Okay, and then you ask the neural network to kind of tune itself in function space, tune its parameters, so that the Yang-Baxter equation gets solved. Right. So in this case, whatever was this deviation from target function is basically the left-hand side of the Yang-Baxter equation. Right? So and then, like I said, yeah, the training is basically tuning the neural network parameters to solve the Yang-Baxter equation. Okay. So of course, so in the same figure, it's not exactly what I drew earlier, but that's also partly because what I drew earlier was wrong. But basically the point is that when you come to the bottom of the hill, I had previously drawn a point for you. But the idea is that here, all the solutions of the Yang-Baxter equation is sitting over here, right? So it's not really a point; it's a basin. And and at the bottom of the hill, basically what the ball would do ideally is to roll around the basin and kind of explore the solution space. And this is indeed what it does. And again, the magic is that this whole thing works. I mean, it's not a priori, it's not always clear that if you do such a thing, and it's a very complicated ensemble of many neural networks being trained with each other without being given any quote unquote help in terms of input output values. It's fairly non-trivial that the whole thing worked. So here I'm drawing for you what actually that a real version of this cartoon. Okay. So here's that index, which is here's that measure, which is essentially the left-hand side of the Yang-Baxter equation, and you can see that like it's true up to 10 to the -4. And in fact, this is also because we stopped over here. We were trying to explore as many solutions as possible, but you could drive it down more in principle. So 10 to the -8 is also achievable. And in this case, I mean, we were looking at two-dimensional spin systems where and R matrices of difference form. So here the solutions are exhaustively known, the analytical forms are known, and we can actually go and compare. And we find that basically when we plot out those functions, they sit on top of each other. What we got by a neural network and whatever is the analytic form, they actually sit on top of each other. Now, of course, in this, there's a lot of jiggery pokery that I'm kind of like hiding away. For example, these are holomorphic functions and things like that, and you kind of want to train the neural network carefully. So all of that I'm just kind of like hand waving away. But the point is that at the end, everything works, kind of like a Bollywood movie. Okay, so far what we've done is to reproduce all known families in this difference form setting. And in what we're doing currently is to look at the generalizations of this approach. How can we solve Yang-Baxter equation in different ways? Maybe new solutions in two-dimensional or three-dimensional, in three-dimensional or four-dimensional spin chains, non-difference forms, things like that. Okay. So that's basically what I had to say about the Yang-Baxter equation. And of course, in this, like you might have seen that what this really utilizes is the universal approximation properties of the neural networks. There isn't anything to machine learn here. There's no data as such. So there is some minimal data, but that's really more in terms of what kind of constraints the R matrix must satisfy. In terms of, you could say, fix what is the Hamiltonian, or which class does the Hamiltonian belong to, or so on and so on.
So these solutions, like, what sense? Like, what are the inputs? What are the outputs?
So the input would be that there's a Hamiltonian. This is the form of the Hamiltonian. You could give it actual numerical values, or you could say that there's a Hamiltonian with undetermined parameters, but where the parameters are constrained in such a way, in a specific way. And this arises from a Yang-Baxter, from an R matrix which solves the Yang-Baxter equation. Given these two inputs, you can get the Yang-Baxter, the full R matrix, and all the higher charges. No. It's yeah, exactly.
One variable depends on another variable?
No. Each of the functions in the R matrix, like you said, it's not one point. It's yeah. So each of the functions is a neural network, and you evaluate it at all possible points. Okay.
So another question is that when you have this kind of thing, it depends on the entries of that 4x4 matrix.
Yes.
Like if the entries are holomorphic and all nice, then you're essentially solving polynomial equations, but it could be meromorphic functions.
Yes.
And then in some sense, you are trying to converge to a divergent function.
Yeah. In fact, that's thanks for making me say things which I didn't want to say. But yeah, that's in fact the main difficulty in training on the complex plane. that you might start with a nice, well-behaved function, but as you tune the weights of the neural network, you might have holes appearing in the. So that's really why we had to kind of like engineer this thing very carefully, that we trained it on the real line, but we designed the neural network so that there's a natural analytic continuation into it. Yeah, thanks for that question. Okay, so yeah, so there's no like I said, there's no machine learning here. So you might ask, okay, fine, you have this nice party trick about how to get solutions, but what about machine learning itself? What about the probable part of the probably approximate framework? Okay, for this, a very general question to ask is that, what would be the utility if you found, say, supposing you did machine learning, you found some correlations in the data. Well, what's the point? And the point is that correlations are predictive. So if you infer a correlation between some input and an output value, you could use that correlation to kind of predict the corresponding value of y given a new value of x. Okay, this is a very rough kind of picture. So basically, for example, if you could infer a correlation that y is a linear function of x or a polynomial function of x, and you could kind of estimate the parameters, then of course, if I give you a new value of x, you can just evaluate it, kind of make a prediction for what is. Okay, but also you can it can give us new insights, and that's really what happens when people try to generate conjectures using this framework, which is that you could ask which features in x are the most predictive of y. Some of them just might be independent. Okay? So let me show you a prototype, and as in all things science, the prototype is a Russian physicist working by himself. Okay, so here is the background. In the 1800s, there was this whole slew of new materials, new elements being discovered, and so some of them were metal, some of them were non-metal, semi-metals, this, that, and the other, and there was really no rhyme or reason to why these elements are the way they are. Okay, and so you might ask that, okay, are the properties of these elements, are they actually random, or are there some underlying principles behind this? And of course, today we know the answer. Today we know that it's because of quantum mechanics and atomic theory. But in the 1800s, we didn't know. In the 1800s, we didn't know this answer. Right? We didn't know about quantum mechanics. In 1890, Erwin Schrödinger was discovering object permanence, not so. Okay, so yeah, so so here's what Mendeleev did, and this is of course building up on work done by other people, but this was really I think work done like beautiful. So I always like to talk about it. So what he did was that he said that, okay, let me try and kind of get a picture of how these elements are distributed, and in particular, let me see how they react with hydrogen and how they react with oxygen. And then he did that, and he found these kind of tables. I haven't drawn the full table for you here, but it's basically just to look at. And what it turns out is that he could infer the properties of say potassium from the properties along this line and the properties along this line. So if you're a machine learning person, this is basically nearest neighbors problem. Yeah. And but more than that, I mean, he could do amazing things. And this is really going beyond this kind of like empiricism. It's like really a triumph of human reasoning. He made some very bold conjectures. So, for example, his prediction of the atomic weight of uranium was something like 240. At that time, the experiments were not so good, so the believed value was 120. So he basically conjectured that it should be 240, which it is. Similarly, I mean, there were some blank spaces in his table, and then he could have just given up and said that, oh, well, this is wrong. But he said that no, I mean, there must be elements of this kind that will later be discovered. And indeed, this was the case. So what is the point of all this? It basically, these kind of empirical studies, what it shows you is that there is a way of organizing the quote unquote landscape of elements into a picture which kind of gives you insights into what kind of trends there are, what kind of families there are. So what are the organizational principles at a very phenomenological level, right? Without going into the nuts and bolts of atomic theory. Okay. And the main takeaway in this is that patterns in known data. So this is why this is not the same as, just stamp collecting and arranging things in a very pretty way. Patterns in your known data give you predictions which are accurate, which are useful on unknown data. So if this whole thing for string theory were to work, this would be the holy grail. Okay. And of course, there's a small caveat here that all this was possible because the size of data and the patterns, they were human comprehensible. It just worked. There were only 56 elements. There were only 2 organizing criteria, and the whole thing worked, right? So what about more principled approaches like machine learning, where you might say that, okay, what about when human intuition breaks down? So, well, I mean, here's a paper from Nature published a few years back, and it's very nice because I kind of made the talk, then I found the paper, and I found that they had actually written this, that his achievement can be viewed as a successful example of feature embedding based on human cognition. Okay, and basically in this paper, what they did was that they used atomic data and some machine learning techniques to kind of group elements together, and they found different realizations of the periodic table.
Wait,
Yes.
let me ask you questions.
Yeah.
So input in that experiment was what? Was it a list of
Yeah, it was.
chemical?
So in this, it was the list of chemicals and their corresponding properties, and it was these are some unsupervised techniques to kind of just basically visualize data, and that's what they found. I kind of I have suspicions about why they found things like this, but let's get back. So right. So but why talk about Dmitry Mendeleev? The point is that such analyses, as I will show you in a moment, are very natural for string theory. Okay. So again, this is kind of like an obligatory slide of how do you get the physical universe from string theory, which is a theory defined in 10 dimensions. And a very popular framework is to say that, well, 6 of those dimensions are Calabi-Yau, and the remaining 4 are whatever is our physical universe. And this is again a little slippery because, as the experts in the audience know actually much better than I do, this needs to be interpreted with some care. Okay, but essentially the point is this, that if you that the properties of the physical universe are dictated by the topology and geometry of the Calabi-Yau. Okay, so basically, if you want to extract 4D physics, you have to tell me what is the Calabi-Yau manifold you're compactifying on. And so it's a very restrictive framework, right? Because if you want to claim something about a 4D universe, you have to find the Calabi-Yau that is going to give you that physics. Okay, there are no 2 ways about this. So which also means that you have to compute across, do a lot of exact computations, including things which we really don't know how to compute, say, for example, the metric. Okay, so in this case, there are many Calabi-Yau threefolds, and the question is which one is ours? And one might ask that, okay, why don't you just compute and see what happens? Well, then when you what happens is that you find that there are 10 to the 500 Calabi-Yaus. That could possibly 10 to the 500 vacua. It's a bit, and I try to find an accurate visualization of how big a number 10 to the 500 is. It turns out that there is no such thing. If you want to estimate the number of hydrogen atoms in the visible universe, that's 10 to the 80. So, I mean, this is like multiplying by 10, 10, 10 again and again. So usually, like when I first saw this number, I thought, oh, it's 500. But no, it's 10 to the 500. So it's,
Wait, what? I thought we don't care about which one is ours. They are all deformation equivalent to each other, and that's all we can say about it.
No, I don't
So,
think
but
so.
what do you mean by which one is out?
I mean, so there's presumably some Calabi-Yau compactification which gives you the right set of massless particles, the right set of gauge interactions which we see in the world around us.
But it's not known, I guess, if there are finite remaining.
Sure, exactly.
Or not.
Exactly. So I'm
That
just
is a long time.
yes. So yes. So let me just come to this point. So imagine that you have kind of a lookup table, okay, where you could just like a Mendeleev periodic table, just put whatever Calabi-Yau you have, put it in the table. From the table, infer what are the properties. Okay, and then when you find the promising candidates that could possibly give you uh, this thing, you could do rigorous computations over there. Now, I agree entirely that, say, for example, it's not even clear what to expect. Right? I mean, usually people go for some kind of grand unification theory, but I mean, who knows, really? Right? And also similarly, like it would be too much to expect that there's only one Calabi-Yau which is giving you exactly that kind of UV physics, but IR physics in this case. But there are kind of ways of uh, like trying to exclude things. Okay. So, and ideally, maybe you could even have Mendeleev like families of Calabi-Yau with exactly which share the same stringy properties. So, in a sense, it would be like taking the vacuum structure of string theory and obtaining very nice organization properties just from observation. Okay, and maybe later at some point, one if a better theoretical framework for describing these vacua comes along, then maybe it could be that there'll be a natural explanation for what these families are. But the same way that quantum mechanics explains why Mendeleev was right. But again, I mean, this is just shameless exploration. Yeah, so let me show you just like this is probably just coming towards the end. So let me show you a very illustrative computation which we did. So imagine the input data. The input data is basically saying how is the Calabi-Yau embedded in an ambient space. This is really the same thing as saying that, say, the round sphere is embedded in R3 as x squared plus y squared plus z squared equal to 1. So what is the locus of points in ambient space that specifies? Okay, so that's and for the experts, the configuration matrices, and the output data is the topology or the number of holes in the Calabi. For the experts, the Hodge numbers. Okay. So what we want is a function that really satisfies this, that it takes as an input this particular configuration matrix, and it tells you what the Hodge numbers are. On its own, this is a very complicated. The standard numerical method runs is double exponential in the number of variables and sorry, 15 cross 16. So this is the size of the configuration matrix. Yes. But yes. So these are CC3. Yes. So we've also done the same thing for CC4. Yeah, but again, I mean, so we are speaking with some people at BIMSA about, say, trying to do this for the Kreuzer-Schacke data set as well. Yes. So great. So like you said, this is CC3. This is also an extreme example. Say permaquintic, this thing is just 5, right? So okay. So the usual way that you would want to find this function is to fix an ansatz and then scan it. Say, for example, you might just eyeball that in terms of y, in terms of x has a particular trend, which is linear or polynomial or whatever, and then yes, yes, it's explicit. But the point is that the computation is double exponential in complexity, and this is actually very illustrative of most computations in this string vacuum. So what eventually would happen is that if you do this on a case by case basis, you will meet some vacuum which is just going to, the runtime will just like diverge to infinity or something. That's basically the point. That this thing runs in polynomial time, and once you've trained it, the prediction is instantaneous. So that was the idea behind the periodic table, saying that okay, if I have a good prediction from the neural network that the Hodge numbers are right, then I can try and do the honest computation and see. Okay. Okay. So the usual way to do this is to fix some kind of ansatz and then scan. But this is a very large input space. And what if there is no obvious ansatz? So here we come back to that claim about neural networks, that they scan across all functions without specifying an ansatz. So again, the idea is that you can use you can have an input function, a function that is basically a neural network which takes as input this configuration matrix, and it outputs the Hodge numbers. Sorry, I seem to be going backwards in time. Yeah. So let me show you what we did. We did a question which is slightly more refined than that. We asked the neural network to find a representation of the Calabi-Yaos such that the Calabi-Yaos that have similar topology, this actually the similar H11 values, are clustered together. Okay, and basically using that, you can we could actually do this. That we could take the configuration matrices that we quote unquote didn't know the answer for, go back, embed it in this auxiliary space, and actually we got very good predictions for what the Hodge numbers are. So it really does work like a periodic. So yeah. So it's, again, of course, it's very preliminary, very skeletal. It's only Hodge numbers. We want to go much further, geometric quantities, Yukawa couplings, so on and so forth. But yeah, at least it's nice to know that a minimal sanity check is working. Okay, so that was the end of whatever I had to say about my own work. Let me just show you a slide about what other people are doing. Say, for example, you have numerical Calabi-Yau metrics being computed from holomorphic neural networks. You can compute quark masses from string theory, which basically involves computing, like we said, the Calabi-Yau metric, the Yang-Mills bundle metric. There are automated methods for finding hidden symmetries of a system. Then there's this recent nice review article which came out a couple of days back, which has a lot of interesting stuff. Again, I don't want to get into the details, but this is just for you to know what is out there. Okay, so here's the summary. So we asked like why probably approximately correct mathematical physics. Well, it can be very useful. You can extract patterns. You can quote unquote organize data, and it's at one level for neural networks. These are very powerful solution finders because it's very easy to scan across function space using. And if you have, say, for example, so you could, at first glance, you could say that, okay, I can use it to get quick estimates of what the answer should be, and which I can then try and later check honestly. Okay. And of course, ideally, it would be that, there's some organization principle that becomes apparent, which gives us some hints of some deep underlying properties. But again, let me say that we are very, very far away from that. Okay. And now I come to the real point of the talk, which is please help me. Okay. As you have seen, there are a lot of uh, uh, different concepts in this, and no sane person can possibly. Okay, so for example, if you are working on probability and statistics, most of our data sets are highly class imbalanced. We have to sample in tails. We have to deal with outliers. If you have principled ways of doing this, please help. If you're working in machine learning and you know how to explore the loss landscape, symbolic regression, reinforcement learning, transformers, please help. If you're working in algebraic geometry and string theory, please help me. How do I best prepare data? What are interesting problems to solve? And in general, what are the other interesting solution spaces to explore? So that's all that I have to say. Thank you.
Questions?
Thank you. So this may be a pretty general question because I always hear about that you can use AI to do anything, but I kind of wondering, like in your reinforcement process, like the process that you are adjusting your approximation and inner functions, anything. Okay, how do you get feedback? Like, how do you know how good your approximation
Right.
is?
It can be different things. For example, if you know the simplest possible thing, which is not the case in our computation, I should emphasize. The simplest possible thing is that if you know the input and output values for some limited subset, then you could say that, for example, the mean square error between the observed output value and the expected output value should be driven down to zero. So there is a lot of subtlety to do with this, which the machine learning and the statistical learning people are well aware of. So I'm not going to push harder on this point. But basically, what you do is that this is a function. The difference, this particular mean square error, is a function of the neural network parameters, right? If you dial the parameters, this mean square error will change. And what you do is that you do gradient descent in the neural network parameters, hoping that eventually you will come down to zero. Again, coming down to zero, there's a big asterisk over there.
So will this property, this requirement, restrict the range of applications of such a method? Like how to tell whether a question could be approximated by the method you mentioned?
Well, yeah, actually, so the question is that how do you tell which problem is machine learnable?
Yes.
So in general, it's not. I mean, I can't give you a practical way. In fact, this title probably approximately correct. It's basically stolen from Leslie Valiant's formulation of when a problem is machine learnable. But it's not easy to tell. Say, for example, if I can machine learn the Calabi-Hodge numbers, and then I intentionally spoil the data set and I just distribute the Hodge numbers randomly, it's a completely insane thing to do, but it's also a data set. And that obviously, I mean, there are just random numbers appearing there. So that cannot be machine learning, right? So it's not, in general, it's not an easy problem. So you have to really try, and you have to try in different ways and then see what works.
Thank you.
More questions?
For lower dimensional topologies, not theory, I'm aware that the data coming from this neural network suggests some nice conjectures.
Yes.
Are you aware of similar things
Yes.
for Calabi-Yos?
In Calabi-Yos?
You're aware.
That would be very interesting.
More questions? Comments? So something that's a very simplified help I can give you as an algebraic geometer. So for instance, if you add more constraints to your search, you might actually learn more. So for instance, these Calabi manifolds, you can say, I'm looking for elliptically fibered Calabi.
Right.
So that obviously searches, restricts your search, right?
Yes.
Have you done that?
So I haven't done it, but people have done it. There are data sets known of elliptically fibered Calabi-Yos, and you can kind of ask the neural network to predict whether it's elliptically fibered or not. It seems to work very well. It seems to work, and yeah, in general, I think it's an important question. Finding out what are the correct set of constraints to impose. Say, for example, you might even for the Yang-Baxter equation, if I just give the neural network the Yang-Baxter equation to solve, usually it collapses onto some trivial solution. So there's a lot of subtlety that I didn't go into, that you have to kind of pose the problem in a way that it actually finds non-trivial solutions. So in that sense, yeah, it would be very, very interesting to also explore maybe different ways of giving data to that's really what I meant. That, for example, if I give say some Hopf algebra structure to the neural network and say that generate a Yang-Baxter equation for a solution for me, things, and similarly for Calabi-Yau.
So without human involvement,
No,
how
yeah,
does your machine learn about? So at least for us in algebraic geometry, we don't. Okay. It's not true to say we don't care how many Calabi-Yaus are there. We care that the moduli space of Calabi-Yau is compact or not, but we also care way more about how many ways we can build the Calabi-Yau manifold. So there are several ways of it: complete intersections, non-complete intersections, elliptic vibrations, things results of degenerations. Is there a way that machine can tell a rather new way of building a new class of Calabi-Yau? But I think it's not possible, right? You just cannot possibly.
an entirely new way of building.
Absolutely. So if you ask an algebraic geometer, classical algebraic geometer, how many ways I can build a Calabi-Yau? Probably they give you 5 ways. That's it.
Right.
Because this is what we tried, and we calculated these Hodge numbers, and it was exactly what it was.
Right.
But then can we actually learn how to build them? Because that's much more important, actually, in my opinion.
Right. Well,
probably the answer is no.
Probably the answer is it's certainly a very sophisticated question. It would involve, say, for example, being able to do the computation for Hodge. Like you could imagine that you start with the general manifold, it's Hodge numbers, and then you try and impose the Calabi-Yau constraint by a machine. But that would involve knowing how to compute Hodge numbers for a general manifold, which is I think much harder. So yeah, in like I would not be optimistic, but I wouldn't say that it can be.
This is something I've been asking people in AI, for instance, Sergey Gukov that you mentioned, which is machine learning is very powerful in checking examples or finding counterexamples.
Yes.
But I don't think it has any whatsoever power to go to a direction unknown to us and find something absolutely unknown, irrelevant of data. It's not possible, right? Why should it be possible? Because it has nothing to do with your ground truth, right?
Well, in some cases, you can prove theorems
with ground truth. Good question. So how it happens with humans, I think, if you ask me, I'll say so many times when people, not me, lucky people, they found these absolutely remarkably new methodologies. The intuition was coming outside of mathematics. Like it was coming from mimicking something they saw in physics or in chemistry. But the machine learning algorithm is being trained on data set of mathematical spaces, cannot do that.
In principle.
Yeah, I mean. Exactly.
Actually,
Professor, yeah, go ahead.
Well, there are many Calabi-Yau. On the other hand, the most interesting Calabi-Yau are those with order number equal to plus or minus 6. If you restrict to those class, can you find how many? Can you find many of them?
Well, I haven't tried. It would be interesting to try. It's yeah.
I only know a few of them.
Right. I mean, now there are pretty robust ways of obtaining Calabi-Yau. Say, for example, this method of getting like this genetic algorithms. It seems to be very impressive. I'm not really an expert in the field, so I can't. I mean, well, this particular subfield of the field, but but at least from listening to their talks, it seems very impressive. It would be interesting to see if genetic algorithms or maybe reinforcement learning can help. Yes.
You have evidence of new Calabi-Yaus, or you have proofs in these new Calabi-Yaus from genetic algorithm? You have just evidence.
No. I think I think they really have new Calabi-Yaus. Yeah.
But either is a new construction or is a particular case.
Well,
It's not a new construction. It's just examples in the same class of construction. That's what I was asking.
Right.
I think it's just hard to imagine the machine tells you, oh, there is yet another way of building.
Well, I mean, okay, if you're really asking me to speculate shamelessly, and I'm going to speculate shamelessly, okay, you have diffusion models which tell you, which are trained on, say, pictures of Einstein and pictures of dogs, and you say that, okay, paint for me a picture of Einstein with a dog, and it can do that. So, or paint for me a picture of a dog, Einstein, and a robot sitting together having tea, and can do that. So it could be like, the kind of thing you're talking about, that, can you borrow intuition from other areas and generate new things? It could, I mean, yeah, it could, but we don't really understand neural networks well enough to make such a bold claim. That's why.
Any more questions? If not, let's thank Shailesh again.
Thanks.